This thing at the very start here is a conjecture we came up with in the last little video. That 1 plus 3 plus dot 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 plus the nth odd positive integer is equal to n squared. That is the square of how many of those odd positive integers we have on the left-hand side. Here is the structure for the proof that I want you to observe and use, especially as you're learning this for the first time. The first thing you want to do is to identify what you mean by P of n to make reference to it. So we will say, let P of n be the statement that 1 plus 3 plus dot 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 plus 2n minus 1 is equal to n squared. This is not going to be phrasing like Pn equals to, I'm not going to use an equal sign here, no, equals to, or whatever, 2n minus 1 is equal to n squared. No, that's incomplete. It only captures the one term on this side. It's the whole sum, and we're going to state it using words like I have right here. This is a well-used phrasing for that. It should be a sentence, and it should start with a word, as I have with let. Having identified Pn, we're going to dive into what we call the basis step, the case where we look at n is equal to 1. And so for that basis step, again, we will use nice sentences, nice, complete, coherent sentences to express it. The way I've written it here is when n equals 1, the statement is 1 is equal to n 1 squared. That's what you get when n is 1. You just get the first term here, and you just get 1 squared on that side. So that's how we would interpret it for n is equal to 1. Even though I know there's a 3 in here in our expression, that's just to give us the pattern for it in the general case. But the first case is just 1 is equal to 1 squared. So I've said what the statement is, and it's very clear that's true, so which is obviously true, thus P1 is true. So that's the basis step. I'll bracket it to show that that statement, that part of the proof, that subproof is completely done. By the way, it would not be counted correct for you to do something like this. N equals 1, that gives us 1 equals 1 squared, check. No, that's not going to make it. No, it's not sentences, it's not clear to the reader. It doesn't describe how you're coming to that or what you're thinking. Okay, so what I've given you there is a much better model to follow. Right, so the second thing is the inductive step to show that if it's true at some integer, it's always true for the next one. That is, we can take this one step at a time, maintaining truth from one place where it's true to the next time, and therefore that would exhaust all the integers where it's true. So the idea here is to select an integer at random, arbitrary is a better word, and assume that it's true. We get to assume it's true because the statement is if it's true at pk, then we get it true for pk plus 1. Okay? So if it's true at some place, then it's true for the next one. So we'll assume it's true for this one place and show it has to be true for the next integer, k plus 1. So the first thing to do here is translate it into what pk is. Well, pk would be to take the first k odd positive integers and sum them, right? And that's what this side is over here. That's the first k of them, and that is claimed to be k squared here. We're assuming this statement is true. Okay, and we're going to then prove that it would be true for the very next positive integer, k plus 1. So off to the side here, I'm going to do a little scratch work. It's going to look kind of messy here, but that's to give you a good idea how to think about this. So over here, I'm going to put a little bar here to make sure you do not put this in your proof. This is on a separate page for you. So this is your scratch, maybe. We want p of k plus 1. So the interpretation here would be, well, I want to add the first k plus 1 positive integers. And the k plus first one is 2 times k plus 1 minus 1. So that's the first k plus 1 odd positive integers. And that the claim is that that's k plus 1 quantity squared. I hope you can read that. This is all just scratch, so we can have that in front of our face, thinking about it probably on another piece of paper. So that's what we want to show is true, assuming what we have over here, assuming what we have right here, that the case where n is equal to k is true. All right, so this is where the challenge will come in. Once you have the structure down pat, the challenge is how to actually go from this statement to that one right there. So it usually takes a little thought and a little consideration what's going on here. Without removing these parentheses, I want to just recognize that since this is the sum of the first k plus 1 odd positive integers, then if I take all the ones before it, 2k minus 1 will be the term right in here. It has this particular sum right there. It's just that it's got one extra term. Now, maybe if we add this term to both sides, we'll be able to get the whole expression there. And that's exactly what we'll do in this case. That will be enough to get us the result. So in the proof, I'm going to now say here, let's add 2k plus 1 minus 1 to both sides. And that will give us, I'll put a colon here to indicate we've done that, 1 plus 3 plus dot 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 plus 2k minus 1 plus 2k plus 1 minus 1. Let me write that a little bit better. K plus 1 minus 1 is equal to, now it's not k plus 1 squared, I don't know that yet. What I know it is k squared, what we had here, plus 2k plus 1 minus 1. I'm getting a little sloppy because I'm filling up the screen trying to explain what I'm doing as we go along here. So, but let's clean up this side right here. This is just using algebra. 1 plus 3 plus dot 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 plus. Now there's no real reason to write that 2k minus 1 term in here anymore. It is there. It's just that we've got all k plus 1 odd positive integers here now. And this side over here is just k squared plus 2k. And then there's a 2 times 1, which is 2, minus 1. So that's plus 1. Or let me reinterpret 1 plus 3 plus dot 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 plus 2k plus 1 minus 1. Again, I'll group that to show it's a single term over there. That's just k plus 1 squared. So we did get what we wanted. All right. This is pk plus 1. Cool. So what does that say? Thus, if pk is true, then pk plus 1 is true. That was intended to be a comma and an if. They're right there. So that right there, let me bracket it in a different color. That's the inductive step concluded right there. Now there's one thing I want to do after we've done the basic step and the inductive step. Let's make an overall conclusion. I concluded inside that inductive step. Let's make an overall conclusion. I'll go back to the green. Therefore, 1 plus 3 plus dot 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 plus 2n minus 1, the original statement, equals n squared. And I have one more thing to say here. Which n is it true for? For all positive integers n. And by the way, notice this is the first time and only time I've used that phrasing in here, because it's the first time any of the statement regarding all positive integers n. So there it is.